We now discuss the eigenfunctions of a Hermitian operator. The eigenfunctions of a Hermitian operator. If, as we discuss, if our spectrum will be discrete, if our spectrum means the eigenvalues of an operator, the spectrum is discrete, as we got such a spectrum in the negative potentials of harmonic oscillator as well as infinite square wave, then those spectra were discrete, and in this situation when a spectrum is discrete, then the eigenfunctions are the basis of Hilbert space. Eigenfunctions constitutes are the bases of Hilbert space, and they actually correspond to physically realizable states, are the physical states of a system. And when the spectrum is not discrete, or we say continuous, as we got for a pre-particle, then in that situation the eigenfunctions are not the bases, or do not constitute a Hilbert space, not the bases of Hilbert space. And they are not normalizable. Such eigenfunctions are not normalizable, and they do not correspond to the physically realizable state. However, there is one exception. However, their linear combination means different states are linearly combined, then their linear combination may give us a physically realizable states. Now, when we are having discrete spectra, for discrete spectra, we have such eigenfunctions of the Hermitian operator, they will have real eigenvalues, as we got in some of the problem, like h psi equals e psi, e is real, and the eigenfunctions that belong, the eigenfunctions that belong to different eigenvalues, which belong to different eigenvalues, are actually orthonormal. Means when we will have, for an operator, when we will have discrete spectra, then the eigenvalues will be real, as well as all the eigenfunctions which will correspond to different eigenvalues, all those eigenfunctions will be orthonormal, means they will be orthogonal to each other and they will be normalized. Now, in case of the continuous spectra, as we discussed for the free particle in momentum space, for continuous spectra, the eigenfunctions are not orthonormal, and they cannot behave like the basis of Hilbert space. For example, if I want to see that whether the momentum operator, for example, minus IH bar d over dx, if I want to find the eigenfunctions and eigenvalues of the momentum operator, then I can write that minus IH bar d over dx of a function, and this function I call f of pp from the momentum and x. So it will give some eigenvalues, let's say those eigenvalues are p, and then fp of x. So now this is the eigenvalue and this is the eigenfunction. So we will have to find out these, and from here we can solve this differential equation, and it will give that f of p of x is some constant e to the power I. It will become I, not minus I, because we are having one minus here when it comes here, and p x by h bar. So we got the eigenfunction like this, but we know that this is not integrable, and we have done some mathematics with this in the previous lecture as we did the Planck-Rule theorem, the Fourier transformation, because the transformation from the real space to the momentum space, and over there we did a lot of mathematics, so I will not go into them. But we have this operator P is having no eigenfunctions in the Hilbert space if it is not square integrable. And however, if we only consider the real eigenvalues, however its value, the eigenvalue is real. So if we consider only the real eigenvalues, then we can just mathematically sort out orthonormality, and let's check how it is done. So this sort of orthonormality is that if I take two eigenfunctions for the momentum operator minus infinity to plus infinity, f of p, and let's say this is p prime and this is another, and we are having this is p and dx. So I can put now the function, the eigenfunction here. So it will be a mod square, an integral from minus infinity to plus infinity, and ei p minus p prime x over h bar and dx. So now this is one sort of orthonormality, because this thing is equal to a squared, and as we did the Dirac delta function, this I can write in terms of Dirac delta function 2 pi h bar delta p minus p prime. So this is sort of orthonormality condition, because when p will be equal to p prime, then it will give us value. Otherwise, if P will not be equal to P prime, then this Dirac delta function will be equal to 0. So this is the Dirac delta function we have done already, so I will not go into the details of Dirac delta function because we have done already these things. So such kind of orthonormality, which seems like orthonormal, these eigenfunctions, so we call that when the spectra will be continuous, then we can have the eigenfunctions not normalizable, but the eigenvalues is real, and they are actually following Dirac orthonormality. Continuous spectra are following the Dirac orthonormality, not the orthonormal cases that we discuss for the bases of Hilbert space. So this way we can write the continuous spectra. We are having the another thing, the generalized statistical, the generalized statistical interpretation. Very briefly, we can discuss the generalized statistical interpretation is if we measure in observable Q on psi x t, then we will get the eigenvalues of this Q operator, and if the eigenvalues of this Q operator will be discrete, then the probability of getting the eigenvalue will be, eigenvalues are Q, and the probability of getting the eigenvalue this much will be Qn, and they will be associated with orthonormal eigenfunctions, which we will call is Fn of x. For example, any wave function I can write is any psi of x, I can write a summation on n Cn psi n. So here Cn is actually the coefficient of it, and this is the mod square of it actually gives the probability of it, and psi n's are the orthonormal bases of the Hilbert space. So these are like unit vectors, and these are like components in vector space, and this is summation on n. Cn mod square will always give us 1. So when this is a statistical interpretation in the sense that we will write a linear combination of this. For example, psi of x will be C naught psi naught plus C1 psi 1 plus C2 psi 2 and so on. If we are only having C naught psi naught in this series, then C naught square will be equal to 1. If we are having up to C1, then C naught square plus C1 square will be equal to 1, and so on. So all Cn square will be equal to 1, and these psi n's, which are actually psi naught, psi 1, psi 2, are the orthonormal bases of the Hilbert space, just like we resolve a vector R. For example, we resolve a vector R into x and I plus y and j plus z and k, or rewrite this is 2 and I plus 3 and j plus 5 and k, for example. So the 2, 3, 5 are actually C0, C1, C2, while I, J, K are Psi0, Psi1 in this. This is vector space and this is the Hilbert space. So we can write our wave function like that.